This portion of the text looks at VHDL and Verilog descriptions of sequential circuits. Both VHDL and Verilog can describe storage elements and sequential circuits. These descriptions involve new code concepts, the most important of which is the process. When we first looked at VHDL, you'll recall that we used concurrent statements for our combinational circuits, but description of sequential circuits with the concurrent statement can be difficult. A process can be viewed as a replacement for concurrent statements that permits considerably greater descriptive power. Multiple processes may execute concurrently, and a process may execute concurrently with concurrent statements. The body of a process typically implements a sequential program. Signal values, however, which are assigned during the process, change only when the process is completed. If we execute the portion of the process shown on this slide, then at the completion of the process, B will contain the original contents of A, and C will contain the original contents of B. In contrast, after execution of these statements in a program such as C++, C would contain the original contents of A. If we want VHDL to have program-like behavior, we can use a construct known as a variable. In contrast to a signal which evaluates after some delay, a variable evaluates immediately. If B is a variable in the statements on the slide, B will instantaneously evaluate to the contents of A, and C will evaluate to the new contents of B. In the end, C contains the original contents of A. Variables appear only within processes. We use := for variable assignment. Here we see a VHDL process description for a positive edge triggered flip-flop with reset. In this code we can see an example of a process. Obviously it begins with the keyword process. Optionally, process can be preceded by a process name followed by a colon. The parentheses following it contain two signals, CLK and reset. This is a sensitivity list for the process. If either of these changes, we execute the process. Following the sensitivity list at the beginning of the process is keyword begin, and at the end, the process keyword end appears. We can also see an example of an if-then-else statement here. The if-then-else within a process is similar in effect to the when-else in concurrent assignment statements. Here the reset is 1, then Q gets assigned the value of 0. You can achieve more complex statements through nesting, just like you would in any high-level language. The other example covered in the text is the sequence recognizer for 1101 that we saw earlier in our discussion of state diagrams. The sequence recognizer has 3 processes, and we can see the first 2 appearing here. Another thing to note here is the appearance of the word type, which permits us to define new types analogous to existing types such as standard logic. In this code, we use it in conjunction with the keyword is to define 4 different states. Here is the second part of the sequence recognizer. If you look at the code in the text, you'll see the use of a case statement. Case statements make a multi-way decision based on the current state of the circuit, A, B, C, or D. The choices must be values that can be taken on by a signal of the type used in the expression. The case statement has an effect similar to the with select concurrent assignment statement. Finally, we see the test bench for the VHDL implementation of the sequence recognizer. In contrast to earlier test benches, this test bench uses more than one process to provide stimulus to the inputs of the sequence recognizer. There is also a for loop to apply the X input value stored in the test to sequence array. To synthesize the circuit into actual logic, a state assignment is needed, in addition to a technology library. Many synthesis tools will make the state assignment independently. They can also do this assignment based on a directive from the user. It's also possible for the user to specify explicitly the state assignment. This can be done in VHDL by using an enumeration type. Verilog can describe storage elements in sequential circuits. In the coming slides, we'll see how this works for the same examples of the positive edge trigger D flip-flop and the sequence recognizer. These descriptions will involve new Verilog concepts, the most important of which are the process and the register type for nets. Like VHDL, Verilog has support for processes. A process is a replacement for a continuous assignment statement that permits greater descriptive power. Multiple processes may execute concurrently, and a process may execute concurrently with continuous assignment statements. Within a process, we use procedural assignment statements. These are not continuous assignments. We need to retain the assigned values over time. We can do this by using the register type rather than wire type for nets. This does not mean that an actual register is associated with its implementation. Additional conditions need to be present to cause an actual register to exist. The type reg is intended for storing values in variables. These can represent either combinational or sequential logic when implemented in hardware. In Verilog, there are 2 basic types of process: the initial process and the always process. The the initial process executes only once, beginning at time 0. The always process also executes at time 0, but executes repeatedly thereafter. For the always process, you can specify a delay using the pound operator followed by an integer, or you can use the ampersand to indicate that you are waiting for an event. The body of a process is like a sequential program. The process begins with the keyword begin and ends with the keyword end. Procedural assignment statements make up the body of the process. Assignment statements can be blocking or non-blocking. Blocking assignments use equal as the assignment operator and are executed sequentially like you would expect in standard programming. Non-blocking use the less than equal as the operator. Non-blocking assignments evaluate the right-hand side, but do not make the assignment until we evaluate all the right-hand sides. Here we see the Verilog process description of a positive edge triggered flip-flop with a reset. Note that we are using if-else conditional structure here. There can be nesting to form more complicated logic if we would like. The other thing to note is an always process that triggers on an event. Inside the parents are the event control statement. The sequence recognizer is much more complex. In particular, there are 3 distinct processes. The module begins with input and output variables for CLK, reset, X, and Z. Next, we declare registers for state and next state. Since next state is assigned with an always block, it must be declared as a register rather than as a wire. We can give state names using a parameter statement as in this example, or using a compiler directive called define. Other things you can see in this code listing are an if-else statement for making two-way decisions and a case statement for making a multi-way decision. In particular, the case statement is useful for states. The sequence recognizer has 3 different processes that interact with one another. The first is the state register, the second is the next state function, and the third is the output. Finally, we see our test bench for the Verilog implementation of the sequence recognizer. We need to consider both the device under test and the register types. The final consideration with sequential circuits and Verilog is the appearance of unexpected storage elements during the synthesis phase. To prevent undesirable latches and flip-flops from occurring, for the if-else structures, we need to take care to include else in all cases if the storage is not desired. In a case statement, we should add a default statement which defines what happens for all choices that are not specified. Thanks so much for watching.